In this section, we're going to look at mirrors and lenses. First, I'm going to define virtual and real images. Okay, so a real image is an image that can be captured on a screen. For example, the image formed by a cinema projector is real. Okay, so this is an image that can be captured on a screen, or you can say it's an image where actual light rays meet, or it is an image where actual light rays meet. Actual light rays meet. Okay, and those kind of images can be captured on a screen because you've got actual light rays meeting at the image. On the other hand, we have a virtual image. A virtual image. This is an image where actual light rays do not meet. It's an image that cannot be captured on a screen. It's the kind of image formed by, let's say, a flat mirror. Okay, so this is an image where actual light rays do not meet. It cannot be captured on a screen. It cannot be captured on a screen. Okay, so example, image made by a cinema projector is real. By a cinema projector is real, and image formed by a flat mirror is virtual. Image formed by a flat mirror is virtual. Flat mirror is virtual. So that's the difference between real and virtual images. So you can see your face on a mirror, but the light rays are just bouncing back. There is no light ray coming from the image that you see. But if you've got an image where actual light rays fall on the screen, then it's a real image. All right, so first we're going to start with mirrors. There are three kinds of mirrors we're going to deal with: a flat mirror and two kinds of curved mirrors. So I'm going to start with flat mirrors. Okay, so let's start with flat mirrors. Flat mirrors. Suppose, let's say we have the following flat mirror. Let's say this is the reflecting side and this is the painted side. Okay, suppose, let's say we have the following object. Okay, so let's try to locate the image of this object. Let's take the tip of the arrow. Okay, so if you take this light ray over here, you see the angle of incidence is 0, so angle of refraction is going to be 0. It's going to return its own path. So the light ray that goes like this is going to return its own path. If you take another light ray that goes like this, you see, in this case, this is a normal line, this is the angle of incidence, so it's going to return this way. Okay, so these two light rays, this one going this way and this one going this way, they're not going to meet on this side. okay? But a person watching from this side thinks the light rays are coming somewhere from here, so it's just a deception. So we have the brain thinking the light rays are coming from here, okay? So in this case, we have a virtual image. You see, this light, the reflected light rays are just bouncing back from the mirror, but the brain thinks the light rays are coming from here. So the brain will see the image of this object at this location. So one of the properties, the image is virtual. The image made by a flat mirror is virtual. No actual light rays over there. It's just a deception. And now if you use the scale, you can see that the image size is actually equal to the object size, okay? So you can say image size is equal to the object size, okay? And then if you compare these two distances, this is the object distance, this is the image distance, okay? If you use the scale, you will see that the object distance and the image distance are equal. The image distance, which is the distance between the mirror and the image, and the object distance, the distance between the object and the mirror, are equal. We call this the object, and this is the image. Okay, so this one over here is object distance, and this one over here is image distance. So if you do this to scale, you will see that the object distance and object distance are equal. The object distance and image distance are equal, and the image distance are equal, okay? Are equal. Well, another property is we can say image is formed behind the mirror. Image formed behind the mirror now. The image is laterally inverted. If you take this object over here, its image would be like this. So the image is laterally inverted, but it's not inverted in the direction parallel to the mirror, okay? The image is laterally inverted. You see? If it is inverted in this direction, but not in the direction parallel to the mirror. This means the image is inverted in a direction perpendicular to the mirror. All right. So these are some of the properties of an image formed by a flat mirror. Okay. Next, we're going to look at curved mirrors. Curved mirrors. These are spherical mirrors. Okay, curved mirrors. First, there are two types of curved mirrors. They're called concave and convex mirrors. There are two types. There are two types. They're called concave and convex. Okay, so we're going to start with concave mirrors. Let's start with concave mirrors. Concave mirrors. In a concave mirror, we have a part of a spherical surface like this. If the painted side is this one and the reflected side this one, is called concave mirror. Okay, if the reflective side is the inside one and if the painted side the outside one, is called a concave mirror. All right, now we're going to define some terms. This is called the center of the mirror. Okay, and then we have another point, the center of, so let's say complete this circle like this. So we have the center of curvature somewhere over here. So let's denote by C. Let's denote this by O. So C is called the center of curvature. Center of curvature. And point O is called the center of the mirror. Center of the mirror. The line through the center of curvature and the center of mirror is called the principal axis. This line over here is called the principal axis. Principal axis. Okay. So the line that passes through the center of curvature and center of the mirror is called the principal axis. Now we're going to define an important point. It's called a focal point. A focal point of the lens. A focal point of the mirror. Of the mirror is a point where light rays parallel the principal axis converge after reflection. This is a point at which light rays parallel to the principal axis, converge after reflection. Okay, so let's take a couple of light rays parallel to the principal axis. Let's say one goes this way. Let's say we have another one over here. Okay, so in this case the normal line is going to be the radius. Okay, so this is the angle of incidence over here, and then it's going reflected back something like this over here. The same thing over here. This is the normal line, which is the radius. Okay, and then it's going to be reflected like this. So you see these two light rays after reflection, they're going to be a certain point that we call the focal point. Okay, so let's denote this by F. So in this case you've got these two parallel light rays meeting at this point after reflection. So this is our focal point. All right, so some properties of this focal point: you've got actual points meeting at the focal point, so the focal point is real. The focal point is real because we have actual light rays meeting at the point. This means actual light rays meeting at the point. And another property is, if you use the scale, you will see that the focal point is located midway between the center of curvature and the center of the mirror between C and O. So the other property is the focal point is located midway between the center of curvature C and the center of the mirror O. Okay, now the distance between the focal point and the center of the mirror is called focal length. Okay, the distance between F and O is called the focal length of the mirror. The focal length of the mirror. Okay, so it follows that the focal length, and we're going to use F for the focal length. So this distance over here is the focal length F. The focal length F. And of course, this is obviously the radius. The distance C and O is the radius of this curvature. This is the radius over here. So it follows that the focal length is half of the radius. So the focal length is half of the radius. the focal length is half of the radius. Half of the radius. So these are some of the properties. Okay, so you get the focal length is radius divided by 2. All right, so next we're going to look at image construction. We're going to look at how to construct images, image construction. But before we look at image construction, we're going to look at light trace that are going to help us to construct images. They're called spatial light rays. Spatial light rays. There are 3 of them. Okay, so let's say we have this concave mirror. Okay, so its center is somewhere over here, the C, and the center of the mirror O. So this is the principal axis. So two of the spatial light rays have directly to do with the definition of a focal point. We've seen that a light ray parallel the principal axis, okay, is reflected back through the focal point. Okay, so that's the first spatial light ray we can use. A light ray parallel to the principal axis is reflected back through the focal point. Okay, so the first spatial light ray is a light ray parallel to the principal axis, is reflected back through the focal point, Okay, so that's one spatial light ray we can use. The other one is the reverse. You see, if you've got a light ray through the focal point, it's going to be reflected back parallel to the principal axis. Okay, so a light ray through the focal point is reflected back parallel to the principal axis. So the second spatial light ray is a light ray through the focal point, is reflected parallel to the principal axis, Okay, so let's say you have this concave mirror over here. Okay, so complete the circle. Maybe the center is somewhere over here, and this is the center of the mirror. Okay, the focal point is located midway. This is F. So if you've got a light ray going through the focal point like this, okay, it's going to be reflected parallel to the principal axis. That's what this spatial light ray is saying. If you've got a light ray going to the focal point, it's going to be reflected back parallel to the principal axis. The third one has to do with the light ray going through the center of curvature. A light ray through the center of curvature, is reflected back in its own path. Okay, so let's say you have this concave mirror over here. Okay, so let's say the center is somewhere over here, the center of the mirror is somewhere over here. This is the principal axis, and this is the focal point. Now, this is the center, okay? So, the light ray is in the direction of the radius, you see? So, the radius in this case is a normal line. You got a tangent line perpendicular to this ray, so that tells you this line, the radius, is the normal line. So, the angle of incidence is 0. That means angle of reflection can be 0. So it goes this way, it comes back its own way, because this is the normal line itself. You see, perpendicular to the tangent line over here. All right, so a light ray through the center of curvature is reflected back in its own path. Okay, so to construct any images, we just need to use a couple of these three special light rays. Now there are three kinds of image formed by a concave mirror, so we're going to look at each of them. Okay, case one, object located beyond the center of curvature, beyond O. Okay, so let's look at that kind of image. All right, so suppose this is the concave mirror, and then we complete this one. The radius might be somewhere over here. Okay, and this will be the center of the mirror. So this is O. This is C, the center of curvature. This is O. This is the principal axis, and then the midpoint between O and P is going to be the focal point. Okay, so now the question is, if the object is located beyond beyond C, beyond the center of curvature, beyond C. Okay, beyond C, where would the image be located? So we're going to use a couple of special light rays. First, we're going to use the light ray parallel to the principal axis. You see, it goes like this. We saw that this goes through the focal point. Okay, this is one special light ray we can use. The other one says a light ray through the focal point, okay, is reflected back parallel to the principal axis. So you see, this light ray going through this point is reflected back parallel to the principal axis. So you see, the image of this point over here, this point, if you observe all the points in the arrow, you will see that the image is this one over here. Okay, so let's look at some of the properties. Now we have actual light rays meeting over here. So this light ray going this way, so it's the image is real because we've got actual light rays meeting over here. So one of the properties is the image is real. And then we see that the image is located between C and F. Image is located between C and F, that is the center of curvature and the focal point. As you can see, it's diminished. It's smaller. Its size is smaller than the object. So you can say it is diminished, and also it's inverted. Okay, it is inverted. So these are some of the properties of the image formed when the object is located beyond O. Okay, so case 2. Object located between C and F. Object located between C and F. Okay, so let's say this is our mirror over here. Okay, this one, and let's say the center is somewhere over here. This is the center of the mirror. Okay, so this is my C, this is my O, this is my F. Now we're saying the object is located between C and F, somewhere over here. This is our object. Okay, and we want to find the image of this object using a couple special light rays. All right, so let's use a light ray parallel to the principal axis, go this way, and then reflect it through the focal point, go like this. Okay, and if we got a light ray parallel, or light ray through the focal point like this, it's reflected back parallel to the principal axis. Okay, so we see that the image is located somewhere over here. Okay, so this is the object, this would be the image. So in this case also we have actual light rays meeting at this point, so the image is real. So another property is the image is real. the image is real. Okay, and what else can we say? You see, the image is located beyond the center of curvature. Okay, image located beyond C. Image located beyond C. Okay, what else can we say? It is enlarged, it is bigger than the object. Okay, it is enlarged. It is enlarged, and as you can see, it's inverted. Okay, you see, it's inverted. It is inverted, and it's located beyond C. I think I already said that, right? The image is real, beyond C. Alright, so these are some of the properties of the image format when the object is between C and F. And then case 3. Case 3, we have object located between the focal point and the center of the mirror. Okay, so let's look at that. Let's say this is our mirror. Maybe the center is somewhere over here. Somewhere here is the center of the mirror. So this is C, this is O, and the midpoint is the focal point. So we're saying in this case the image is located somewhere over here. Okay, so let's look at the properties of this one. Now if you've got a light ray part of the principal axis, it goes through the focal point like this. Okay, how about if you've got a light ray going through here like this, through the focal point like this? It's going reflected parallel to the principal axis. So you see, this goes this way, this goes this way, it goes this way, this one is going this way. So these two light rays are not going to meet on this side, but the brain thinks these light rays are coming from a point somewhere over here. Somewhere over here. Okay, so the image is going to be over here. Alright, so this is a virtual image because we don't have light rays over here. The light is going to be reflected from here. It's just a deception, but the brain thinks these two light rays are coming from a certain point over here. Okay, so one of the properties, the image is virtual. We don't have actual light rays over here. The image is virtual. No actual light rays meeting at that point. What else? The image located behind the mirror. The image appears to be behind the mirror. Appears to be behind the mirror. Behind the mirror. And you can see that it's erect. It is erect. And it is enlarged. It is enlarged. So these are some of the properties of the image when the object is located between the focal point and the center of the mirror. Okay, so these are the properties of a concave mirror. Next, we're going to look at a convex mirror. Convex mirror. Convex mirror. Okay, so this is a case where the painted part is the inside and the outside is the reflecting part. So in this case we have a mirror, just something like this. Okay, so in this case the painted side is the inside and this is the reflecting side over here. Okay, so let's say the radius of the center of curvature is somewhere over here. So it's going to be our center of curvature. This is going to be the center of the mirror, and the line connecting these 2 points is called the principal axis. So you got O over here, you got C over here, and this is the principal axis. Principal axis. Okay. Now we're going to define the focal point. Okay, so the focal point of a convex mirror this is the point from which the light rays seem to come. The light rays seem to come after reflection. Okay, so let's look at is a point from which I should say light rays parallel to the principal axis. Let me add over here, parallel to the principal axis. Okay, light rays parallel to the principal axis seem to come after reflection. Okay, so let's look at a couple of parallel light rays. Let's say this is a light ray parallel to the principal axis, and this one is a light ray parallel to the principal axis. Okay, now you see the normal line is the radius. This is the normal line, is the radius over here. Okay, so this is the radius, so this is the angle of incidence. This is going to be reflected like this. It's going to be reflected like this. The same thing over here. This is the radius over here. Okay, so this is the angle of incidence. It's going to be reflected like this over here. All right, we'll go like this. So these two light rays, this one, obviously they're not going to be on this side, but they seem to come from a certain point over here, and that's what you call the focal point. So you see there are no actual light rays, but the light rays are just coming this way and being reflected, coming this way, being reflected. But for somebody on this side, it looks like the light rays are coming from this point. So this is the point from which the light rays parallel to the principal axis seem to come from after reflection. So some of the properties are: the focal point is virtual. There are no light rays over here. It's just a deception. Okay, the focal point is virtual. The focal point is virtual. And if you use the scale, you'll see that the focal point is located midway between O and C. The focal point is midway between the center of the mirror and the center of curvature. Okay, so in this case we do not have a real focus, we have a virtual focus over here. Okay, so this light rays parallel to the principal axis, they go like this. This one goes like this, but the brain thinks the light rays are coming from a certain point over here, and that's what you call the focal point. All right, now we're going to look at image construction, but before that we have to look at the special light rays that are going to help us to construct the images. Okay, so we're going to look at image construction over here, image construction. But before that, we have to look at spatial light rays. There are 3 light rays that can help us construct an image. Okay, a couple of them have to do directly with the definition of focal point. So you see, a light ray parallel to the principal axis seems to come from the focal point after reflection. That's the first one. Okay, so the first one is a light ray parallel to the principal axis, seems to come from the focal point after reflection, from the focal point after reflection. Okay, so let's say this is our convex mirror. So this is the painted side. And then let's say this is our principal axis over here. So if you've got a light ray parallel to the principal axis like this, okay, and let's say this is my O, this is my C, this is my focal point. After reflection, the light ray seems to come from this point like this, okay. So a light ray parallel to the principal axis seems to come from the focal point after reflection. All right, and then the second one is the reverse of this. A light ray directed towards the focal point is reflected parallel to the principal axis. A light ray directed towards the focal point, is reflected parallel to the principal axis, parallel to the principal axis, Okay, so let's say we have this convex mirror. So let's say the center of curvature is from over here, and this is O. This is O, this is C. And the midpoint is the focal point over here. Now if you've got a light ray directed towards the focal point like this, it is reflected parallel to the principal axis. That's what this light ray says. I mean, this special light ray implies. Okay, the third light ray has to do with a light ray directed towards the center of curvature. You see, if you've got a light ray directed towards the center of curvature like this, you see this is the radius, which is a normal line. So it's going to return its own path because the angle of incidence is 0 and angle of reflection is going to be 0. So the third one is a light ray directed towards the center of curvature, towards the point C, is reflected in its own path, All right. So suppose we have the following convex mirror. This is the paint side. Let's say center of curvature is somewhere over here. This is the center of the mirror, and the focal point is somewhere over here. Now, if you've got a light ray directed towards the center of curvature like this, you see, this is the radius is the normal line because perpendicular to the tangent line over here. So the angle of incidence is 0, angle of reflection is going to be 0, so it's going this way, it's going to return its own way. So a light ray directed towards the center of curvature is reflected in its own path. So these are the special light rays that are going to help us construct images. We just need a couple of them to construct images. There's only one type of image for this kind of mirror. So let's look at image construction. Okay. Let's look at constructing image. There's only one type. Okay, so let's look at the property of that image. So let's say this is our convex mirror. Okay, this is the painted side over here. So maybe the center of curvature is somewhere over here. And this is point O, and the midpoint we have the focal point, okay? And this is the principal axis of the mirror. So let's say we have an object located over here. So we're going to use a couple of the of the special light rays to construct images. So if you take a light ray parallel to the principal axis, what's going to happen? After reflection, it will look like it's coming from the focal point, so it'll go this way. Okay? And how about a light ray directed towards the focal point? If you've got a light ray directed towards the focal point like this, it's going to return parallel. Okay? So you see, we've got these two light rays. One going this way, one going this way. They're diverging. They're not going to meet on this side. So somebody looking from this side will think that these light rays are coming somewhere from here. So this is the image. Okay, so we don't have actual light rays in this case. The light rays are being reflected on the surface, but the image is behind the mirror, just like flat image. Okay, so the properties are: the image is virtual. The image is virtual. Okay, and then as you can see, it is located behind the mirror, located behind the mirror. Okay, as you can see, it's diminished, it's smaller, it is diminished. It's also erect. Okay, it is erect. So these are the properties of the image formed by a convex mirror. All right, now we're going to look at the mirror equation. Mirror equation. You can also predict the properties of the image mathematically. Okay, so let's look at that. Okay, now first we're going to define some terms. Let me use maybe a concave mirror. So let's say we have this one over here. Okay, this is the concave mirror. Okay, so the center of curvature is somewhere over here. This is the center of the mirror, and you get the focal point in between. Okay, so we've seen that if the object is somewhere over here, and then the image will be somewhere over here. So this distance over here is called the object distance. We use P to represent it. And this distance over here, the distance of the image and the center of the mirror, we're going to use Q is image distance. So P is object distance, which is distance between the object and the center of the mirror, and Q is image distance. Image distance between the image and the center of the mirror. And then this distance over here is called the focal length, which is distance between the focal point and the center of the mirror. So this is the focal length. Now, these three quantities are related by the following. 1 over the focal length equals 1 over object distance plus 1 over image distance. This is what we call the mirror equation. Okay, this is the mirror equation. But it's very important to know when to make the variables positive or negative. So let's look at sign convention. Sign convention. A focal length, this one over here, is taken to be positive if the focal point is real, and it's taken to be negative if the focal point is virtual. So focal length is taken to be positive or negative if the focal point is real or virtual. Okay, so focal length is taken to be positive if the focal point is real, and it's taken to be negative if the focal point is virtual. So we know that the focal point of a concave mirror is real and the focal point of a convex mirror is virtual. So it follows that focal lengths of a concave or convex is positive for concave, negative for convex, okay? Because we know that the focal point of a concave mirror is real and the focal point of a convex mirror is virtual, okay? How about image and object distance? These two values, image and object distance. Okay. Object or image distance is taken to be positive if the object or the image is real, and negative if the object or image is virtual, okay? So in this case, if the image is real, the image distance is taken to be positive. If the image is virtual, the image distance is taken to be negative. The same thing about the object. If the object is real, the object distance is taken to be positive. If the object is virtual, the object distance is taken to be negative. You might ask, how can the object distance be virtual? That's possible, for example, to have double lenses. You can have the image from by one lens, which is virtual, serving as the object of another lens. So it's possible to have double lenses, okay? So these are the sign conventions for the variables, all right? The focal length is positive for concave mirror, negative for convex mirror, and object distance and image distance are positive if the object or the image is real, and negative if the object or the image is virtual, all right? And then let's define magnification. Magnification is defined to be the ratio between image size and object size. This is ratio of image height to object height, okay? Object height. So if you use h naught for object height and h image for image height, and if I use m for magnification, then I have the following formula for magnification. Magnification equals the size of the image divided by the size of the object, okay? And we have also sign convention for the size of the object, size of the image. They're taken positive if they're erect and taken to be negative if they're inverted, okay? So the sign convention for H and HI and HO is HO or HI is taken to be positive if the object or the image is erect, and negative if the object or the image is inverted, okay? So these are the sign conventions for the heights. They're taken to be positive if they're rect and negative if they're inverted. So if you obtain negative value for the height of the image, it means the image is inverted. All right. Now it can also be shown that the magnification is also the ratio between the negative of image distance to object distance. Okay. So magnification is also equal to the ratio, or to the negative of the ratio of image distance to object distance So we have also the following formula for magnification: negative of image distance over object distance. Okay, so now let's look at an example. Okay, let's say an object, let's say of size 2 centimeters is placed at, let's say, 6 centimeters in front of a convex mirror, let's say whose radius of curvature is, let's say, 4 centimeters. Okay, the question is A, calculate the image distance. All right, so let's write what we know. The size of the object is 2 centimeters. Okay, that's HO equals 2 centimeters. And then what else do we know? It's placed 6 centimeters in front of a convex mirror. So 6 centimeters is object distance. So P equals 6 centimeters. Now we're told the radius of curvature is 4 centimeters of the mirror. Okay, so you've got radius equals 4 centimeters. Okay, so we know that the focal length is half of the radius. Okay, so we know that that's going to be 4 over 2 centimeters, but this could be positive or negative. But we know that the mirror is convex, therefore the focal length is negative. So our focal length is negative 2 centimeters. All right, and the question is calculate Q, image distance. So you've got 1 over F equals 1 over P plus 1 over Q. All right, so the focal length is negative 2, so you've got 1 over negative 2, and this one is 1 over P. Object distance is 6 centimeters. Object distance is, that's P is 6 centimeters. Okay, plus 1 over Q. Okay, so 1 over Q equals negative 1 over 2 minus 1 over 6. Okay, so this is negative 3 over 6 minus 1 over 6. That is a negative 4 over 6, but this is an inverse, we got inverted, so Q equals negative 6 over 4 or negative 3 over 2. Okay, so what does the negative mean? The negative means the image is virtual. Okay, so the negative means the image is virtual. The negative means the image is virtual. The image is virtual. All right, now let's calculate the magnitude. Let's say calculate the size of the image. B, calculate the size the size of the image. Okay, so you want to calculate HI. And the formula relating size of image and size of object is magnification equals the size of image divided by the size of the object. Okay? But we also know magnification equals negative Q divided by object distance. So this is the negative of image distance is negative 3 over 2. So you've got negative 3 over 2 divided by object distance, which is 6. Okay? So that is 3 over 12 or 1/4. Okay? So the magnification 1/4, which means the size of the image would be 1/4 of the size of the object. Okay, so from this equation we get the size of the image is magnification times the size of the object. The magnification is 1/4. The size of the object is 2 centimeters over here. 2. So the size of the image is half centimeters. All right. Next, we're going to look at lenses. Lenses. Okay, a lens is basically a piece of glass with spherical surfaces. Okay, a lens is a piece of glass with spherical surfaces. Spherical surfaces. Okay, and there are two kinds of lenses. There are two kinds of lenses. Okay, one is called convex, or sometimes called converging lens, and the other one is called concave lens, sometimes called diverging lens. Okay, so we're going to start with convex lenses. Convex lenses. All right, so let's say we have the following convex lens over here like this. Okay, so let's say the center of curvature for this one is over here. Let's say the center of curvature for this one is somewhere over here. Okay, let's call this maybe C1 and C2, and this line connecting these 2 points is called the principal axis. This line over here is called the principal axis. Now the process in this case is refraction. For mirrors the process was reflection, but in this case the lights are going through. This is glass. Okay, so let's define now a focal point. If you remember, focal point has to do with the convergence of light rays parallel to the principal axis. So if you take a light ray parallel to the principal axis like this, okay, they're going to be refracted. All right, so because of refraction, this is going to bend, and we'll go to a certain point over here, and then this is the same thing over here. Because of refraction, the light is going to bend. So this point over here, where light rays parallel to the principal axis converge after refraction, is called the focal point. Okay, so let's define the focal point. The focal point, or F, this is the point at which light rays parallel to the principal axis. We're talking about this light rays parallel to the principal axis converge after refraction through the lens. Okay, so let's look, let's say this is the center of the mirror over here. Now let's look at some of the properties for this kind of focal point. You have actual light rays over here, so obviously the focal point is real. Okay, so one of the properties of the focal point is the focal point is real. The focal point is real. And the other property is, if you do this to scale, you'll see that the focal point is located midway between the center of the lens and the center of curvature. Okay, so the focal point is located midway between the center of the lens, okay, which is O, and the center of curvature, all right. All right. I think I would think about mirrors. Let me take this one off. Let me take this one off, but I'm not sure. I don't think that's true. Let me take this one off. That's true for mirrors. All right. We're going to see later how the focal length and the radius of curvatures are related. This is true for mirrors, but not for lenses. All right, let me take that off. All right, I was thinking of mirrors. All right, so next we're going to look at image construction. But first we're going to look at special light rays. The light rays that will help us to construct images. Special light rays. Okay, the first to have directly to do with the definition of focal point. A light ray parallel to the principal axis is refracted through the focal point. So the first one is a light ray parallel through the focal point, a light ray, a light ray parallel to the principal axis, is refracted through the focal point, Okay, so there is this light ray over here. A light ray parallel to the principal axis is refracted through the focal point. The reverse is true. A light ray through the focal point is refracted parallel to the principal axis. Okay, a light ray through the focal point is refracted parallel to the principal axis. All right, so the second one is the reverse of this one. A light ray through the focal point, is refracted parallel to the principal axis, Okay, the third one has to do with a light ray that goes through the center of the lens. If you've got a light ray that goes through the center of the lens over here like this, you see the bending on the surface is going to be compensated by the bending on this surface, and it'll go straight. Okay, so a light ray through the center of curvature passes straight and deflected. So a light ray through the center of the lens, the center of the lens passes and deflected. Okay, it passes straight. So these are the special light rays that we have as to construct images. We just need a couple of them to construct image. Okay, now we have three types of images. So we're going to look at three cases. So case one, we're going to look at object located beyond twice the focal length. Okay, so we're going to look at an object located twice beyond the focal point. So let's say this is our convex mirror. Let's say this is our principal axis, like this. So let's say this is our focal point over here, and then let's call this point a distance of twice the focal length by 2f. Okay, twice the focal length. We have the same thing over here. We got f over here, and twice the focal length over here. Let's call it 2f. All right. So in this case, the object is located beyond twice the focal length, somewhere over here. Okay. So let's look at the image of this object. If you use the first special light ray, a light ray part of the principal axis is refracted through the focal point, like this. Okay, is refracted through the focal point, and a light ray through the focal point over here, like this, through the focal point, is refracted parallel to the principal axis. So you see, this is the size is exaggerated. So let me. So it might be something like this. I know it's going to be smaller, so I didn't draw it properly. So this is the image over here. So let's look at some of the properties. You see, the image is located between f and 2f, located between f and 2f. Okay, and it's real. We've got actual light is over here, so the image is real. The image is real, and then it's inverted. It's inverted and it's diminished. Okay, so these are some of the properties of the image formed by a convex lens when the object is located beyond 2f. All right. Case 2. Case 2. Okay, object located between f and 2f. Object located between f and 2f. That is the object distance between one focal length and twice the focal length. All right. So let's use this one. Maybe this is my principal axis over here. Okay, let's say the focal points over here and twice the focal points over here. The focal point over here, twice the focal point is over here. Now we're saying the object is located over here. Okay, so let's look at the properties of the image. So you've got a light ray part of the principal axis. It goes through the focal point like this. And if you've got a light ray through the focal point like this, it goes. So you see the image is somewhere over here. All right. So this is 2f. This is the image over here. So the image is also real. So we have the image is real. We have actual the image is real, and it is inverted. It is inverted. You can say located beyond 2f, located beyond 2f, and it's also enlarged. It is enlarged. Okay, it is enlarged. So these are some of the properties of the image formed by a convex lens when the image is formed between f and 2f. All right. Okay. And then object located, case 3. Object located between the focal point and the center of the lens O. Okay, so let's say we have something like this. Let's say it's our lens. So maybe our focal points are, let's say, over here and over here, over here and over here. So this is F, this is 2F, this is F, this is 2F. It looks exaggerated. And then let's throw this line. So in this case, our object is located somewhere over here. All right. So let's see what happens. A light ray parallel to the principal axis goes through the focal point. Through the focal point like this. Okay. And a light ray through the center passes undeflected, right? So it goes like this. It passes undeflected. So you see these two light rays diverge. They're all on the side. But for somebody looking from this side, it looks like these light rays are coming from somewhere over here. Okay? So this is the image over here. So in this case, the image is virtual. No actual light rays over here. The light has been reflected this way, but it looks like they're coming from here. So the image is virtual. The image is virtual. And as you can see, the image is enlarged. The image is enlarged. And you can say it is erect. It's erect. And you can say it's formed on the same side. Formed on the same side. Okay, so these are some of the properties of the image formed by a convex lens when the object is placed between the focal point and the center of the lens. Next, we're going to look at concave lenses. Concave lenses. Okay, this lens looks something like this. Okay. All right. So this is the center of the lens. And then we got curvatures over here, some over here. The curvatures are over here, and this line is called the principal axis. This line is called the principal axis. Principal axis. Okay. Now we're going to define the focal point. The focal point has to do with light rays parallel to the principal axis. Okay. So in this case, the light ray is going to diverge and go like this. And then we have a light ray over here is going to diverge. So this light rays do not on this side, but they look like they're coming somewhere from a certain point over here. So this is the focal point. So it's the point from which light rays seem to come from after refraction. So it's virtual. So let's define the focal point. The focal point. This is the point. The point from which light rays seem to come, especially light rays parallel to the principal axis, parallel to the principal axis, principal axis seem to come from after refraction, after refraction. So we do not have a real focal point in this case. The focal point is real. So the focal point is virtual, it's not real in this case. We do not have actual light rays meeting at the focal point. All right, now we're going to look at image construction. But before we do that, we're going to look at spatial light rays. Okay, now the first two have directly to do with the definition of focal point. So the first one is a light ray parallel to the principal axis seems to come from the focal point after refraction. So a light ray parallel to the principal axis, seems to come from the focal point after refraction, from the focal point after refraction. Okay, and the reverse is true. If you've got a light ray direct towards the focal point, it's refracted parallel to the principal axis. If you've got this light ray directed towards the focal point, it is refracted parallel to the principal axis. So the second one is a light ray directed towards the focal point. The focal point is refracted parallel to the principal axis. Okay, the third one has to do with the light ray that goes through the center of the lens. If you've got a light ray that goes through the center of the lens like this, you see the bending over here will be compensated by the bending over here just go straight. Okay, so a light ray through the center of the lens passes undeflected. So a light ray through the center of the lens, passes undeflected. Okay, so these are the three spatial light rays we can use to construct images. There's only one type of image for a concave lens. So let's construct the image. Constructing the image. Okay, so let's say this is my concave lens. Okay, let's say this is the principal axis over here. Let's say my object is somewhere over here. Well, I'll put the focal points maybe over here. Okay, so let's say the object is located somewhere over here. Okay, so let's see what's going to happen. So if you've got a light ray parallel to the principal axis, it seems it's coming from the focal point, right? It'll go like this. And you've got a light ray through the center, it will pass undeflected. Okay, so these two light rays, obviously they're not going to meet on this side, but for somebody looking from this side, it looks like the light rays are coming somewhere from here. Okay, so this is the image over here. So this is not real, it's just a deception. Okay, it looks like the light rays are coming from here. So the image is virtual. The image is virtual and it is erect. It is erect. It is diminished, and formed on the same side. Formed on the same side. On the same side, okay? So these are some of the properties of this kind of image. But we can also do this mathematically using the equation they call the lens equation. So we're going to look at the lens equation. The lens equation. Okay, the lens equation is identical to the mirror equation. So let's say if you use the convex lens like this. So let's say this is F, this is 2F, this is F, this is 2F over here. Now I've said that, let's say this is our object and we said the image would be somewhere over here. So this distance over here is object distance P, and this distance over here is image distance Q, and this distance over here is focal length F, as you've seen before, right? And that equation is 1 over focal length equals 1 over object distance plus 1 over image distance, all right? And the same sign convention applies, okay? F is positive or negative if the focal point is real or positive, real for positive and virtual for negative. Okay, so that's the sign convention for the focal length. But we know that the focal point of a convex lens is real and the focal point of a convex lens is virtual, so it follows that F for a convex or concave lens, so it's going to be positive for this one, negative for concave. Okay, all right, the same thing for P and Q. P and Q are positive if the object or image is real, and they're negative if the object or the image is virtual. So P and Q, like this is P or Q, is P and, let's say P and Q are positive if the object or the image is real, and negative if they're virtual. Okay, the same thing as before. So object distance is positive if the object is real, negative if the object is virtual. The same thing about Q. Q is positive if the image is real, and negative if the image is virtual. All right, and then sign convention, magnification. If the size of this object is HO, the size of this object is HI. Magnification is defined to be the size of the image divided by the size of the object, but also is equal to negative image distance divided by object distance. Okay, so M is magnification, and these are the size of the image and object. All right, now example. let's say an object of, let's say, size maybe 2 centimeters is placed, let's say 8 centimeters in front of, let's say, a convex lens whose focal length is, let's say, maybe 10 centimeters. Okay, so A, calculate its image distance, calculate its image distance. Okay, so what we have is the size of the object is 2 centimeters, is placed at 8 centimeters, that means P is 8 centimeters. Okay, and the focal length, you see, for a convex lens is positive, is 10 centimeters. Okay, so we have to find Q. All right, and the formula is 1 over F equals 1 over P plus 1 over Q. Okay, so we've got 1 over 10 equals 1 over 8 plus 1 over Q. All right, so 1 over Q is 1 over 10 minus 1 over 8. Okay, so that is 4 over 40 minus 5 over 40, that's negative 1 over 40. Okay, so 1 over Q is negative 1 over 40, that implies Q is negative 40 centimeters. Okay, let me see if, all right, so we've got 1 for columns, 1 over 10, this is 1 over 8. Okay, 1 over 10, this is 4 over 40, and this is 5 over 40, so you got negative 1 over 40. The image, I mean, the Q is negative 40, which means the image is virtual. Okay, now B, calculate its magnification. All right, so M is negative Q over P, negative Q over P. So Q is negative 40 and object distance P is 8. So the magnification of this one is 5. All right, C, calculate the size of the image. Okay, so we're looking for HI in this case, but we know that HI divided by H naught, the size of the image divided by the size of the object, is magnification, which we already calculated 5. So the size of the image is 5 times the size of the object, which is 2 centimeters. Okay, so the size of the image would be 10 centimeters. Okay, so finally we're going to look at Lensmaker's equation. Lensmaker's equation. Now this is a calculation based on the radius of curvatures. So let's use convex lens as an example. So let's say we have this lens over here. So this is the center of curvature over here, which means this is the radius of the surface over here, and then we have the same thing over here. Let's say center sum over here, and this distance over here is the radius of the second surface. Okay, so this is surface 1, this is surface 2. Okay, so this is our length. These are the radius of curvature of the first surface, and this is the radius of curvature of the second surface. And we're going to use n for refractive index of the glass. Refractive index of the glass. Okay, then the lens maker's equation is given by the following formula. The inverse of the focal length equals the refractive index minus 1, and then 1 over the radius of surface 1 minus 1 of the radius of curvature of surface 2. This is what we call the lens maker's equation. Okay, so n is refractive index, and this is our radius of curvatures of the first surface and the second surface. Okay, so now let's see when we make the radius positive or negative. Okay, sign convention. Sign convention for the radiuses. Sign convention for the radius. Okay, so if the direction from the surface towards the center is the same as the direction of the light rays, let's say the light rays are coming from here. Okay, if this direction is the same as the direction from the surface towards the center, the radius is taken to be positive. But let's take this surface. The light rays are coming from here, but the direction from the surface to the center is this way. Okay, so the radius of curvature for this one will be taken to be negative, but the radius of curvature of this one will be taken to be positive. Okay, sign convention. So a radius is taken to be positive if the direction from the surface to the center of curvature is the same as the direction of the light rays. As the direction of the light rays. And it's taken to be negative if these directions are opposite, and it is taken to be negative if these directions are opposite. If these directions are opposite. Okay, so let's look over here. For this surface over here, you see the light is going this way, and the direction from the surface is centered this way. So R1 is going to be positive in this case. The radius of curvature of surface 1 is going to be positive. Okay, therefore this implies R1 is positive and R2 is negative. That is for a convex lens. How about for a diverging lens? A diverging lens would be like this. So this is surface 1, this is surface 2. Now let's say the light rays are coming this way. Okay, now the direction from surface 1 towards the center is this way. Okay, so we take this radius to be negative, but for this one the light rays are going this way, the light rays are going this way, and from the surface or center this way. So in this case, you see R1 would be negative and R2 would be positive. Okay, so for a convex lens, the first surface will be positive if the light rays are coming from the left. R1 will be positive, R2 will be negative, but for diverging lens, R1 will be negative and R2 will be positive. This is for concave. Okay, let's look at an example. let's say a lens is made of glass of refractive index, let's say 1.5. okay, the radii of curvature of the two surfaces are, let's say, 4 centimeter. Okay, so the question is calculate the focal length A if the lens is convex. So we have this convex lens. Okay, the radius of curvature are 4 centimeters. So you've got absolute of R1 is 4, absolute value of R2 is 4. Now, let's say the light rays are coming from here. You see, for this surface, the direction from the surface toward the center, the surface 1, the surface 2, is going this way. So R1 is positive, it's 4. But for this surface over here, you see the direction from the surface toward the center of curvature this way. So R2 is negative 4. Okay, and then of course Rn is 1.5. So the focal length is n minus 1 over focal length equals n minus 1 over R1 minus 1 over R2. Remember, the focal length for convex lens is expected to be positive, right? So you've got 1.5 minus 1. R1 is 4, so you've got minus 1 over negative 4. Okay, so this turns into plus, right? 1.5 minus 1 is 0.5. Then this turns into plus, we get 2 over 4, or half. Okay, so this is 1 over 4. It follows that the focal length is 4 centimeters. All right. B if the lens is concave. B if the lens is concave. Okay, so in this case, we have this lens like this. All right. So let's say the light rays are coming from here. This is surface 1, this is surface 2. Now, for surface 1, the direction from the surface center is this way. So these directions are opposite. So that tells you R1 is negative now. Okay. But for this surface, you see the direction from the surface center is this way. The light is going this way, so R2 is positive 4. Okay. So the focal length is 1 over focal length equals n minus 1 over R1. Remember, the focal length of a diverging lens is expected to be negative. So you've got 1.5 minus 1. 1 over R1 is 1 over negative 4, and then minus 1 over 4. Okay, so you've got 0.5. This is negative 2 over 4, or negative 1/2. So you get negative 1 over 4, and follows the focal length is negative 4 centimeters.